We're the 2022 Oklahoma State Capstone Argonia team, the Space Cowboys. The challenge of the competition is launching a rocket 8,000 feet above ground level and delivering a golf ball-sized payload using a vehicle deployed from the rocket as close to the target on the ground as possible. To take on this challenge, we broke our teams into 3 different sub-teams. Our propulsion sub-team focus is split between the rocket and its motors and the propulsion system of the recovery vehicle. A lot of its time has been spent simulating, picking, testing both the rocket and the deployment of vehicle's motors. The structure sub-team is in charge of building and assembly the body of the rocket and the body of the recovery vehicle. They designed and are going to test it to make sure that its structure will handle the competition. Our avionics sub-team is running the rocket avionics bay and the recovery vehicle's avionics. Both of them include both navigation and telemetry.
After many trade studies, research, and discussions, our team decided to design a quadcopter vehicle to carry the golf ball payload as close to the landing site as possible. The main advantage of using a quad is accuracy, which is very important in a target-based mission. For the current design of the quadcopter, our team went with an H-style vehicle with a carbon fiber frame. It has plenty of room for our electronics, and the slim body will allow it to fit nicely into the rocket body. The arms are also spring-loaded to help with deployment. The rocket design was influenced by past competition years, but tweaked slightly to fit our exact needs. The fiberglass rocket will be about 8 feet long and an outside diameter of 4 inches. This gives us enough space for all avionics, recovery components, and a payload.
Our team will be flying a 4-inch diameter fiberglass rocket on an L-class impulse motor. The rocket is made up of 3 sections, a 36-inch booster, a 40-inch payload section, and a 16-inch nose cone. The booster and payload sections are connected by the avionics bay, with the nose cone being connected to the payload bay by an additional coupler. We will be storing our quadcopter in the payload section. Deployments will be conducted via black powder charges initiated by the Altus Metrum, Telemega, and Easy Mini flight computers. After a drone deploys, it will make its way to the landing site, while our rocket descends under drogue and main parachutes safely at 30 feet per second.
On the structure side of things, our main objective was creating a fitted payload integration for the quad that also allows for smooth deployment after ejection. The structure of the quad was aimed to create a compact avionics layout around the golf ball payload that allocates for folding space for arms, motors, and propellers. With all this in mind, we decided to go for an H-shaped quad with sandwiched avionics as a base iteration.
For our recovery vehicle design, we decided to do a fully autonomous H-style quadcopter with the option for manual control through an FPV camera feed and a handheld controller. Throughout the design phase of our quadcopter, our team used the website eCalc to size our motors, ESCs, propellers, and a battery to best fit the mission requirements. To get the most endurance, we went with a lower kV motor in the range of 1700 to 2200 and are experimenting with props from 6 to 7 inches that will also give us the best flight performance we are looking for during the mission. Due to the 4-inch rocket diameter, space is a very large limiting factor for the quadcopter, and the layout and configuration must be optimized to make everything fit. Because of this, our team selected a flight stack configuration for the flight controller and a 4-in-1 ESC, and also utilized nano configurations of transmitters and receivers.
SOLIDWORKS allowed our team to determine if designs were feasible and to quickly iterate upon designs to meet the task. For example, a member of our team could develop a design option, such as a bracket mount, and it could quickly be turned into reality through SOLIDWORKS. This allowed us to lay out avionics and have an idea of spacing for the components, while also giving us an accurate center of gravity location. Our team utilized 3D printing of brackets that perfectly fit onto our designs. Motor mounts and spring mounting brackets allowed for the quadcopter to deploy and operate much more smoothly.
We are doing off-the-ground testing and mid-air testing with our quadcopter to ensure the feasibility of the design. These tests will help determine how it holds up in varying wind resistances, the thrust and power available throughout flight from our propellers and motors, the durability of our frame, as well as the real battery life of our avionics system. Our rocket is undergoing drogue deployment testing as well as integration testing to see where our quadcopter deployment mechanism has the most likeliness to fail and how we can fix that risk.
So this is our first iteration of the quadcopter prototype. As you can see here, it's made out of stock carbon fiber pieces. However, in the future, we're going to be changing all of our structural stuff into composite material. This is carbon fiber in the 40-90 degree orientation with balsa wood in the middle. But for now, this serves as a good purpose for us to begin collecting data necessary for sizing our prototype down in the future. Another thing to note is that we are going to be adding spring-loaded arms in our future iterations. So when it is in the rocket, the spring arms come out. These bulky bolts are going to be replaced with these M4 screws in the future to help with weight and also keep the structural integrity of the prototype together.
Thank you for watching our video. We're excited to see you in Argonia.
Go Vols!